All right. Thank you, folks, for your attendance today. Really appreciate that. This is our first, and I hope, of many series of these Lunch and Learn webinars. Before we get started, everyone, please take a moment to note a safe path of egress for any emergency. Please refresh your memory on where you might have a first aid kit, an AED device, a fire extinguisher. Just be mindful of your path of egress, your muster points. Please just take this call if it's safe to do so. Unfortunately, in this time, day and age, we need to be cognizant of active shooters. So our company policy is specifically to run, hide, and fight. My grandpa told me that a good run's better than a bad stand, so I'm going to be a runner. But you guys, be mindful of that. The best time to prepare for his emergency is now when you don't have one. So just be mindful of that. As an HP warning, our error-likely situations occur for us typically on the last day of a work week and just before lunch or just after lunch. This is a prime human performance error-likely situation, so just be mindful. Our minds are engaged in what we're going to do this weekend or what we want to get finished this week. So just take a moment to familiarize yourself with the path of egress and any safety protocols that you guys may need to adhere to. And with that, let's just jump right into it. So today's topic is CVT Alarming Methods. It's capacitive voltage transformers. What I have shown on the screen is two different types of what I would call the one on the left is a CVT, a capacitor voltage transformer, and the one on the right is a coupling capacitor voltage transformer, CCVT. Now, they're often used synonymously. The difference is the one on the right typically has a few more accessories with it. It has a wave trap, a line tuner, and it is used to couple a 10-watt, 22-volt carrier frequency signal directly onto the transmission line. That always fascinated me as a young engineer. So the devices are very similar and same. The one on the right has a few more accessories. It has a drain coil, an additional ground coil. But for purposes of today's topic, CVT and CVT are essentially the same device. They work the same way. So a little bit about Duke Energy. For those of you that are probably in our service area, we're a large utility, large customer-owned utility. We have, a presence in 6 states now, several million customers. And we have in service just in this area, in the upper portion of North Carolina and South Carolina, 3,000 of these devices. We use these things for metering, for protection, for control. So they're a very prevalent device, and it's a very cheap, economical way to step down your nominal transmission voltages, 100 kV, 230 kV, down to a usable value. And that's why we use them. So, again, we're a large investor-owned utility. You guys are probably served by us that are in North and South Carolina, or your co-ops are. So, and we're happy to present today. So what do we want to talk about? We're going to just cover basically what is a CVT, how does it work, why should we monitor for these things, and then how do we do it? We're going to cover the what, whys, the hows, and see what we can come up with. So I hope you find this at least informative somewhat, and we're looking forward to having other topics for other disciplines that you guys may be interested in. So with that, what is a CVT? The textbook device definition is it's a capacitive voltage device used to step down transmission class voltages for use in relay protection and metering. What you have here is this is a simple one-line diagram. This is the terminal where you'd have your line voltage hooked up to, be it 100 kV, 230 kV, even 525 kV in the case of Duke Energy. And basically, it is a voltage divider. It uses a capacitor stack to divide your voltage down from your line to ground voltage down to a usable voltage down here in an inductive pot down here at the bottom. Typically, at this point, you can have between 5 kV and 11 kV feeding your inductive transformer. Then on your secondary terminal, this is where you have your 120 volts that feed your relays, your meter. And so it gives you an accurate representation of the primary voltage and the quantities there in a secondary term. So it's a very cheap way to step down your voltage. It consists of a capacitor stack that's a voltage divider. It has this compensating reactor. This basically, if you have a voltage source, you come from a normal voltage source, you go to a capacitive voltage source, you have this reactor that switches that phase angle back to where it was. It's just, capacitive is at 90 degrees, so this just switches it back. That's kind of the basics, the very basic thing, a very basic device. Here's what it does. So here we have the 20, the line voltage hooked here, and we reduce it down to 12, 5 kV to 12 on 100 kV and 230 kV. This is at 12,000 volts is what we use. We also, on the coupling capacitor voltage transformer, we also have some ferroresonance suppression circuits in here and some drain coils. And what they're used there to dampen your signals that you may get from any type. If you have a delta line, a long delta line, you tend to have capacitance from your long line to earth. So you have some ferroresonance circuits in here that dampen those harmful signals that cause heating of your devices. And again, the L1 is used to compensate for your phase angle shift from a capacitive voltage. Very simple. This part right here is oil filled at the bottom of it, and your stack has oil in the top of it where the insulators are housed. Again, yeah, it contains a spark. On that secondary side, I just showed you has a spark gap arrestor. That's for any type of overvoltage you may see on your line. And then, as I mentioned before, we have these ferroresonant networks that protect or dampen harmful signals. And at the beginning of the presentation, I showed you that we have these combination of wave traps and line tuners that we use to couple our signals for carrier protection. Basically, you'll see that on any transmission distance line, you'll have some type of carrier protection, be it a directional comparison blocking or POTT or something such as that. So it's a really neat device. It's been around a long time. We have, 3,000 more in service just in this service area. And they're relatively inexpensive, about, $20,000 a piece as compared to a full inductive transformer type that you could see some places. So why monitor an alarm? Well, the obvious reason is we want to prevent this here. If you look in this red box, that's where a capacitive voltage transformer was. It was sitting there. I want you to pay special close attention to the debris field. This is the debris field. Look at where when it disintegrated, it shot shrapnel. It shot the porcelain insulator that houses the capacitors. This is about a 50-yard debris field. You can see where it was on fire. It caused some burning, very catastrophic failure. And this, guys, if you think about it, guys and girls, if you think about it, anytime you have a failure of this device, it causes your bulk electric system to have an operation, okay? That's going to impact your customers, your power quality, your CMI, and if you notice that it threw shrapnel everywhere, it could potentially damage other equipment, okay? It could hit, if there had been a breaker here, it could hit the bushing. You can see the fire it spread out here. It's definitely hazardous to any employee that would have been there in the yard. So the main reason we do this is we want to prevent this. We want to prevent these random end-of-life events and prevent this catastrophic failure is the main reason. It's for our human safety, and it's also to protect the bulk electric system. When you have operations of your bulk electric system, it tends to, your mistakes will be found out. If you have any settings errors, you can have misops, and that's inert reportable. So it's very advantageous to monitor and alarm to prevent these catastrophic failures. So, so in my experience, these CVTs, they telegraph well in advance, weeks, months of imminent failures. What they do is a typical common failure mode for these capacitive voltage transformers is the capacitors in that stack will either short or go open. So think about this. If you have a fixed amount of capacitors and you lose one, that same voltage is expressed across less capacitors, which tend to, cause more stress on the existing capacitors and they start to fail. So they don't typically fail all at once. It's a gradual thing. So this is this is something we can exploit. We can exploit the fact that a common failure mode is the capacitors, they short to go open. They do it one at a time, then another one before they have a catastrophic failure. And this happens, again, it happens weeks and even months prior to that failure event. I mentioned to you before the violent failures, they spray oil. And I guess the physics of the matter is it shorts, pressurizes that stack, and you saw how violent that failure was. You have, electrical forces, you have pressure forces, you have gas forces from the oil expanding. So it's just a very, very hazardous condition. It's one we want to prevent. For us, in our industry, most of these devices are 20-plus years old. These are active devices. They're on the system constantly. They've been exposed to transients, and now they're near their end of life, okay? I mentioned to you earlier that these events, they result in unwanted operations of your bulk electric system. That's the customer outage minutes. That's Power quality issues for your customers, allergies for your customers. It's never a good thing to experience that. You don't believe me, go to California where they've been out of power for a couple of days now, and they're screaming and hollering. So we don't even like our power to blip, much less be out for any extended period of time. So another reason why we should monitor an alarm, it's relatively easy. It's an easy thing to do. It's an easy thing to exploit, and it's an easy thing to take advantage of. So that's why we do it. That's why we want to do it. So how do we do it? Okay, very simple. A couple methods we're going to talk about today. Zero sequence alarming is one of my favorites. Very simple. We can take advantage of the concept. You look over here, VA plus VB plus VC will sum to zero if all those magnitudes are equal. Okay, that's a concept we all learned in school. So how can we exploit that? If we have electromechanical relays, okay, typically the windings of the CVT have one winding that feeds your protection, another winding that may feed your backup protection, and a third winding that goes unused. Okay, you can take that third winding on each phase, and you can configure that into what I call a broken delta. Okay, you can take one winding from each phase, series them together, and you can break that delta right there, and you can install a relay. Set it for 10 volts, have an output to alarm your local screen. As long as VA and VB and VC are alike, we have nothing. But if we lose the capacitor stack in VA, the voltage could go up or go down. Now we have a current flowing in that delta, and that current provides a resistance across that relay. It picks up an alarm, so it's relatively easy. It's required some wiring, some low skill set right here. All you need is to series the windings, run some wire and a relay and output, and tie into your system. And we use this zero sequence alarming on we have electromechanical relays. This is our go-to source. We use these for our bus voltage indicators, where we don't typically tie into a relay. So it's a very simple circuit, very easy to do. And this is how we deploy it. This is an example where we had a CVT that was alarmed locally for a week, okay, zero sequence alarm. This is the event recorder that it was printing out. It's telling you had a 74's alarm, voltage, ground, and SMs for the South Mountain. This is just one snapshot of the event recorder paper. It literally ran paper, just ran page after page after page. It kept alarming. Look, it was alarming every few milliseconds. It was alarming, just typing out. So this is an example where the zero sequence alarming actually caught an event prior to the catastrophic failure, and we call this a success. Okay. Here's what happened. We were interested in the analysis, the extended condition of the device. So this is the bottom section. Typically, this would be oil field. This is your inductive transformer we looked at earlier. Some of this is your ferroresonance suppression circuits. What we saw here was really astonishing. This is the 11 kV lead that you have. Mind you, this is in oil, so it doesn't arc. But what you saw was evidence of old arcing in the tank down there. An old carbon path was being built. And you saw a new, hard bolted, hard fault there. The carbon path was relatively new. Okay, so what it did, what we found was in the tank that heated that when it saw that short. There's that resistor in there that's part of the ferroresonance network. It blistered and it sprayed oil out of the corner right here. Okay, the short heated it. It caused blistering, and then we sprayed a little bit of oil out on the tank. The key point here is the CVT did not fail catastrophically, and I ought to mention to you that the thing was in alarm for about 2 weeks before the techs ever got out there to it. So I believe that we could have even prevented this from happening had we responded sooner. It's kind of an out-of-way location. It wasn't a very close location, and they didn't see it as a high priority. But that was a lesson learned for us that when these things alarm, we need to respond a little quicker. But I'm calling this a success because it wasn't a failure. It wasn't a catastrophic event. It didn't operate the system. We caught it before any real damage was done. So how do we do it for alarms with microprocessor relays? Again, this is a higher skill set. You need some logic settings and your PNC guys. It doesn't take any wiring. It doesn't take any hardware. Your stuff's already embedded. So I've just showed here like a 3-step method. You create logic settings for the microprocessor relay. You add display points for your local enunciation at your station, and then you incorporate this setting into your I/O summary so you through your SCADA system, and you can notify your transmission control center of the real-time, lifetime status of your devices. So this is kind of a three-step process. And again, it's a higher skill set, but it doesn't take any hardware to do that. Typically, your stuff's already in place. So how do we do it? Now, I put this slide up here just for you relay guys, you relay nerds. Normal people don't like this. We don't like to look at relay settings like this, but I'm going to try to step through the logic setting. I have 3 slides that basically depict the same thing. This is the actual settings that we use. The next slide will be your logic settings on a diagram, and then more of a GUI, kind of an interactive, more of a pictorial view of what we're talking about. So what you have in and typically we use SEO relays. They're numeric relays. They're easy to set, and we just deploy our logic. So what you do, this is a variable, PNV01. We take voltage, B phase, fundamental instantaneous magnitude, okay? We add that to C phase, fundamental instantaneous magnitude. So we got a snapshot of B phase and C phase. We divide by 2. Hey, that's the average. We take the average of B phase and C phase, okay? We assign that a variable. Then we take that a variable, and then we say, is it 10% above or below, okay, and we multiply it by 0.9 or 1.1. We assign that as another variable. So what we've done, we took the average of B phase and C phase, okay. We've multiplied it by 10% above and below right here. We compare that average to a setting of 53 volts. Now, this is important because an alarm setting is different than a loss of potential, okay? A loss of potential, if you lose the secondary voltage, you need to take different action than if you alarm. If you lose it, sometimes we like to accelerate our zone 2 setting. Sometimes we like to block our carrier. So 53 volts is the point we say, okay, if you're at 53 volts, you have a loss of potential. So that value is tied with an AND gate, okay, and it's compared to A phase. Remember, I took B phase, C phase, I averaged them out, okay. I've got a variable that's 10% above, 10% below. Is this average greater than 53 volts? If it is, it fires an AND gate, and I compare that AND gate with A phase fundamental magnitude of the other variables, okay? And that is an alarm. If it hits that OR gate, that is the alarm. I do the same thing for A to C, compare it to B, A to B, compare it to C, okay? Does that make sense? I know that it's hard to follow, and I despise these logic settings, but that's what it is. These are the actual settings, but we'll look at a picture and make a little more sense in just a minute. So I've got average of B phase and C phase. I compare it to A phase. Is it 10% above or below? Is it greater than 53 volts? If it is, I alarm. If not, I move on. Again, a loss of potential is different than an alarm. This drawing is a little bit better, okay? This is B phase, C phase. I've averaged them, okay? Is it greater than 53 volts? I fire an AND gate, all right? I take A phase. Is it 10% above or below? If it is, that satisfies the equation. That hits the AND gate. That's one input. I did the same for the other phases. I hit a timer. Boom, I have an alarm, okay? Make sense? Same thing for A to C, same thing for A to B, okay? It's the average. Is it 10% above or below the phase that you didn't measure? And then if it satisfies the AND gate, boom, it's an alarm. Here's the picture I like. It's simple, okay? B phase, C phase, I add them, I divide by 2. I multiply by 0.9. I compare it to 53 volts. If it's greater than that, I satisfy the AND gate, and the same thing. So this is 3 ways of looking at the same thing. Basically, that's your logic settings. We incorporate those logic settings into the relay, and at that point, that satisfies the first part. I've got the logic settings. I've got them created. I've downloaded them in the relay. What else do I need to do? I need a display point for our local enunciation, okay? If the CVT that feeds this relay is an alarm, I want to display that, okay? So if that equation was satisfied, I see a CVT alarm on the rolling display of that specific relay, that specific line. And that's how that tells the operator when he gets there, hey, this is the line that's in trouble. This is the one I need to look at, okay? Excuse me. So the final piece of this is I need to incorporate that this was the output setting for the alarm into our SCADA settings, all right? This is a relay. So if the South Mountain line, if it's in alarm, it's a 1. If it's normal, it's 0. If I satisfy that equation that we saw earlier, the logic settings, I send a high to my SCADA system, and I send that alarm. This alarm is my control center at a remote location. This way I can take immediate action. I can deploy my resources, my techs. They know exactly what to go to. Okay, I've got an alarm on the South Mountain, CVT, send alarm, and they'll go there and they will address the issue, be whatever it may be. So let's talk about what we talked about. All right, in summary, CVTs, they are capacitive voltage type transformers. They're used to step down a transmission class voltage, typically 100 kV, 230 kV, even 525 kV. We use them for metering applications, for protection applications, for control applications. They supervise reclosing, they initiate swap overs. So they're a very useful device. They're a very inexpensive way to step down transmission class voltages, to use them for these applications. All right, they consist of a capacitor stack. We talked about how they're made. They got a capacitor stack that acts as a voltage divider that feeds an inductive transformer at the bottom. The good news here, they almost always indicate failures by experiencing voltage swings, which can be monitored and provide alarming preceding an event. We can exploit the fact that they do this, and we can get it. Key here is preceding an event. That's the goal. We want to prevent this from a catastrophic failure, so we can do that. We talked about a couple methods we can do it. We can alarm locally with simple zero sequence circuits. It's a low skill, takes a little bit of hardware and some wiring. Or we can do it with microprocessor relays, a little higher skill set. You need some logic settings and someone that can issue those logic settings into the relay and commission those things. We can add those settings and alarm points into our SCADA, which gives us remote access. And we looked at one case where this approach has been successful in identifying and mitigating catastrophic failures. So with that, guys, we have a few minutes for a good question, and a good question is one that I have an answer for. So if you don't have a good question, hold it. So let's see. Hostel, should I go to the chat screen, or what do I need to do for the answer the questions?
All right, there's one question from Hasala Dharmavardhana. The question is, do you use inductive VTs in your system? The accuracy of CVT can get challenging, especially for measuring very short transients.
Yes. So yeah, absolutely. We use inductive VTs for many things and many purposes. We like inductive VTs for metering. Our meter guys prefer them because the losses are less. 44 kV and below is our preferred method for a potential transformer, which would be an inductive type. They're hermetically sealed. They're oil filled. They have a relatively small footprint in the station. As you get above 44 kV, 100 kV and above, it doesn't become cost effective to use an inductive type. They're so huge, they're cost prohibitive. So the majority of utilities at 100 kV and above will use some type of CVT is typically where it is. So the DMARC basically is based upon your voltage class. But yes, absolutely we use them for metering applications, potential applications for over/under voltage schemes. But basically they're at 44 kV and below for more of a distribution class stuff. And thank you for your question. Well, folks, I appreciate your time. I appreciate your attention. We're open to any ideas for any future webinars. Appreciate you coming out today. And if there's no more questions, okay, here's one. What are the maintenance testing activities you perform? All right, excellent question, because I have an answer for that. Thank you, Balney. So we have every device we have on our system has a maintenance activity associated with it. And it's typically, at the old school, it's time-based. But moving forward, I think we're going to move towards a more condition-based. So maintenance activities, typically for the CVT, they are infrared monthly, okay? When you install them, you commission them, you use a power factor test. The power factor test determines the loss, the I-squared all losses of the insulators, and also gives you a good ratio test. But we have a maintenance activity for every type of instrument transformer that we have. For CTs, we do Megger testing, we do ratio saturation, we do polarity, we do all sorts of commissioning tests. We do station walk downs monthly, and also we use an infrared yearly, and it's a thermography camera, of course. And what that does, it can preemptively more of a condition based. But I tell you what, we're looking at doing now. There's a lot of emphasis on health monitoring. Everybody and his brother now is making devices that check partial discharge, that check losses such as that. And ideally, any company would want to maintain their equipment the day before it's due to be destroyed. We don't want to spend any money to do that. But there's lots of things on the market now that we're looking at. But yes, we have maintenance activities. They're mostly time based, and we may be moving towards more of a risk base. Thank you for your question.
We have 14 more minutes. We can answer a few more questions. There's a
Sure,
question from
sure.
Side.
Yeah.
I'll read out the question for you. So some of the relay use bulletin capacitive voltage transform supervision element. Is also provided to detect a voltage error due to a capacitor short-circuited in a CVT. The relay detects a permanent small zero sequence voltage and gives an alarm, adjust timer. Can this be used for same purpose?
So for what purpose are we talking about? The relay detects. So we have the numeric relays that also numerically calculate the zero sequence in there. It's a real easy math function to do, especially for a numeric relay. Adjustable timer, yes, our timers are adjustable. Is this IS? This can be used for the same purpose. What is IS? I don't understand what IS stands for. I don't understand the acronym.
Right, can you explain more your question? Until that, we can go for Walney's second question. For ratio test, what is the minimum voltage used?
So what we use, our double test sets are 10,000 volts. And we just would work the ratio back from that. We put a 10,000 volt on the primary and calculate the ratio, which is typically 9:10 to 1 on the secondary side for a 100 kV line. Simple math. But in addition to the ratio test, we double test the windings in it to make sure that we don't have any losses. Some of you use bulletin capacitive voltage transformer supervision. I'm not sure what bulletin capacitive voltage transformer supervision elements provide to detect the voltage.
He might be referring to built-in CVT.
Oh, built-in. So we use predominantly SEL relays, okay, and those relays you can configure. The settings I saw you were actual settings that we developed and deployed to the relays, and it's for it does the math for you, but also there's a zero sequence what you call a pre-packaged design or setting in the relay itself for zero sequence, and I don't exactly remember how they do that. I'm not really a relay PNC guy. I have an interest in it, but I'm not. It wouldn't be my discipline. But I know that there is a pre-can setting with the SEL relay, so I suspect it looks at all three voltages and does the math for you. Would be my guess. But that's we could find out from the SEL manufacturer's bulletin if we need to. And the relay does detect a small zero sequence voltage. It does give an alarm. It absolutely works for both a zero sequence issue on those SEL relays. I've seen it. I'm not exactly sure of the mechanism by which the zero sequence is done in the relay, but I strongly suspect it's a math function provided from the inputs of the voltage.
And there's a side also asking the purpose of detecting failures in the CVTs.
So the purpose is, if you saw that picture, the reason we want to detect a failure is we don't want to experience a catastrophic failure. What that does, it sends shrapnel, fire, it damages equipment, it causes an outage, it's hazardous to the employees, it operates your bulk electric system, it presents a whole other problem. So the purpose of detecting the failure in the CVT is to prevent that catastrophic failure.
Another question?
the question about phase. So each of our relays has a voltage input and a current input, so it's very simple to detect the phase. It can measure the phase between phase to phase, a phase of the current, so it's very simple. The numeric relays do an excellent job to detect the phase deviation of anything. It looks, and then when you think about it, think about the zero sequence. If you have a VA plus VB plus VC that is all balanced, you have no, your zero sequence current, there's nothing flowing in that path, okay? So how do you check the phase deviation? It's going to be, if the current flows, that one phaser has gotten out of alignment with the other one. So that by definition, that's going to give you a phase difference and a current flow in the delta. But again, the SEL relays do that mathematically. Excellent question. Yeah. Do the accuracy of CVTs vary with time? That's a fantastic question. I'm glad you asked that. So this is old school. The CVT's been around a long time. The old CVTs used a paper, cellulose paper that provided the insulation between the capacitor elements. So over time, absolutely, they varied. This is your 80s, your 70s, and your 80s vintages CVTs absolutely vary with accuracy. It was a problem. You saw very few metering applications back from 70s and 80s because the meter guys complained. But what they did now, they gone to a Nomex type paper that they use. It's not even a paper; it's a polymer. So the accuracy of the CVTs, the life expectancy is 20 years. Typically on our system, they're about 25 years, and the drift is. It was a problem in the old days. It's not so much a problem now because they use better quality Nomex paper to make them with. It's a polymer paper. It's not the old cellulose paper. So the accuracy is not a concern over time. It's the fact that they've been in service for 20 years and they've been exposed to every transient on the system over that time, and they degrade. And so that's the problem we have. But accuracy for us is not an issue. But we do alarm for that. But for the new style trench and other manufacturers, they use a different paper in there on the capacitor stack, so they're much better. So does the logic work if there's some unbalances in voltage in the system? If you know, and that's an excellent question, and the reason I say that is because I have an answer for it. So there is a timer in there. Once you satisfied the equation for alarm, it goes to a 120 cycle timer. That's a minute or so. And what that timer does, that is just for that. It's for any type of disturbance or under voltage you may have system wide. So you have say your system experiences a fault down the road, the generator sees it, your voltage sags for a period of a few cycles. You don't want an alarm in that case. So we add a timer to that. It has to be that condition. Once it's satisfied, it has to hit that flip-flop timer for 1,200 cycles before it actually alarms. And that's how we overcome the unbalances in the system. So you're exactly right. We do that through a timer. All those outputs, the final path before it alarms is a timer. So thank you for your question. And again, I think, Hassa, will this presentation be available to the guys of our chapter? That would be glad for them to look at to have access to the presentation. They can look at the logic and they can just really digest what we're doing here. I think it would be helpful if they're interested in it and you're okay to make it available to them. I would be okay with it.
Yeah, we recorded the presentation, so it will be available in the web.
Awesome. Well, guys, look at that. Syed, if you would, look at the logic setting, follow logic through, and you'll see that there's a timer at the very end of it.
All right. If there's no more questions, thank you very much, Joe Tynan, for this initiative, Lunch and Learn Education series. And thank you all for participating and actively asking questions and getting clarifications. So we'll be back with the second edition of our series. Thank you all.
Awesome. Thank you, guys, and look forward to seeing what you guys have to present for us. Take care and have a great weekend. Have a safe weekend. Thank you.